Flow measurement is critical in oil and gas, power generation, chemicals, and water treatment. A flow transmitter measures how fast a fluid moves through a pipe and converts that into a 4 to 20 milliamp signal. In this video, we cover the working principle and calibration of a differential pressure flow transmitter connected to an orifice plate. A DP flow measurement system has two major parts. The primary element, an orifice plate, creates a pressure difference inside the pipeline. The differential pressure transmitter receives the high and low pressure signals through impulse lines, calculates delta P, and converts it into a standard electrical output. High pressure side is marked H, low pressure side is marked L. An orifice plate is a thin metal plate with a precisely sized opening. When fluid passes through the restriction, velocity increases and static pressure drops. The pressure upstream is higher than downstream. This difference is called differential pressure, or delta P. Delta P equals P high minus P low. The transmitter senses this difference through the impulse lines. The relationship between differential pressure and flow is nonlinear. Flow is proportional to the square root of differential pressure. At 25% dP, flow is 50%. At 50% dP, flow is 70.7%. 100% dP gives 100% flow. Square root extraction is configured inside the transmitter or in the control system. The transmitter outputs a 4 to 20 milliamp signal. 4 milliamps is the live zero, representing zero flow. 20 milliamps represents 100% flow. The live zero lets the control system distinguish between zero process flow and a wiring fault or power failure, a critical safety feature in industrial measurement. Example, a transmitter calibrated for 0 to 1,000 millimeters of water column, representing a flow range of 0 to 100 cubic meters per hour. At 0 dP, the output is 4 milliamps. At 1,000 millimeters water column, the output is 20 milliamps. When square root extraction is enabled, intermediate points follow the square root calculation. Before calibration, obtain the work permit and complete isolation and lockout procedures. Confirm the process fluid, pressure, and associated hazards. Isolate the transmitter and depressurize impulse lines through the approved vent connection. Never loosen process tubing while pressurized. Calibration must only be performed by trained and authorized personnel. Required equipment includes a traceable pressure calibrator or hand pump, a precision loop calibrator or multimeter, a 24-volt DC power supply, suitable pressure tubing, and a HART communicator for smart transmitters. All reference instruments must hold a valid calibration certificate with accuracy suitable for the transmitter being tested. Connect the pressure source to the high-pressure port of the transmitter. For bench calibration, the low-pressure port may be open to atmosphere. Connect the 24-volt supply and milliamp measuring instrument in series. Verify polarity before applying power. For very low dP ranges, use a differential pressure calibrator connected to both ports for better accuracy. Apply zero differential pressure. For a manifold-mounted transmitter, open the equalizing valve with both process sides isolated. This places equal pressure on both sides of the sensing element. Allow the output to stabilize and record the as-found reading. Expected output is 4 milliamps. If the zero error exceeds tolerance, perform a zero trim. Do not adjust the calibrated range to correct a zero error. Apply 0, 25, 50, 75, and 100% of the calibrated pressure range in sequence. Record the output at each step. Then decrease through 75, 50, 25, and 0%. The downscale pass identifies hysteresis and repeatability problems. Error equals measured output minus expected output at every test point. When square root extraction is active inside the transmitter, the applied pressure points are different. To simulate 25% flow, apply 6.25% dP. For 50% flow, apply 25% dP. For 75% flow, apply 56.25% dP. Always confirm where square root extraction is configured before evaluating your results. If the transmitter is outside tolerance, Identify the error type before adjusting. A consistent zero shift needs a zero trim. An incorrect span needs sensor trim or range verification. A milliamp output error needs analog output trim. Use the HART communicator and follow the manufacturer's procedure. Never change the range values as a substitute for proper sensor calibration. After calibration, close all vent and drain valves. Slowly open the high-pressure isolation valve while the equalizing valve remains open. Then close the equalizing valve and slowly open the low-pressure isolation valve. Inspect all connections for leakage. Confirm the transmitter reading is reasonable before returning the loop to normal operation. Calibrating the transmitter alone is not enough. Verify the complete measurement loop. Compare the transmitter local display with the value in the PLC or DCS. Confirm the engineering range, square root configuration, alarm set points, totalization, and control response. Any scaling mismatch between the transmitter and control system must be corrected before the loop returns to service. A successful transmitter calibration does not guarantee accurate flow measurement. Errors can still come from a damaged or incorrectly installed orifice plate, blocked impulse lines, process fluid density changes, poor pipe geometry, or control system misconfiguration. A complete flow system assessment must cover the primary element, process conditions, installation, transmitter, and the control system calculation. A differential pressure flow transmitter measures the pressure difference created by a restriction in the pipeline. Flow is proportional to the square root of that pressure difference. A complete calibration requires isolation, zero verification, upscale and downscale testing, adjustment only where needed, safe restoration, and full loop verification. Following the correct procedure ensures accurate measurement and plant safety.